Hello everyone, happy learning. As you can see here, we already cover benchmark test functions and the important role of benchmark test functions in optimization. Today, in this video, we will understand how we can calculate mean and standard deviation of benchmark test function for any optimization algorithm. And we will use here a numerical example to calculate mean and standard deviation of benchmark test function for any optimization algorithm. So first question is why benchmark test functions are used in Meta-heuristic algorithms. So first we will start with why benchmark test functions are used in Meta-heuristic algorithms. So we use Meta-heuristic algorithms when traditional methods either fail or they take too much time to solve any problem. So Meta-heuristic algorithms like PSO, genetic algorithm, ACO, Firefly algorithm, BAT algorithm and all. So here you can see we have a number of Meta-heuristic algorithms that we can use to solve optimization problems, complex optimization problems, even real life optimization problems. So here you can see we have a number of Meta-heuristic algorithms because according to no freelance theorem, there is no single algorithm that can solve all type of optimization problems. This means that an algorithm that is giving you best results for one type of problem, same algorithm can give you poor results for other type of problems. Suppose we have here two algorithms, algorithm A and algorithm B, and we have 5 different optimization problems, 1, 2, 3, 4 and 5. Now we will apply these two algorithms to solve these problems. Here you can see algorithm A is giving us best result for problem 1, 2 and 5, and at the same time it is giving us poor results for problem 3 and 4, and algorithm B is giving us best result for problem 3 and 5, but it is giving us the poor results for other problems. That's why according to no freelance theorem, there is no single algorithm that can solve all type of optimization problems. That's why every year researchers propose new optimization algorithms because no single algorithm can work well for all type of problems. So new algorithms are created to solve different challenges in areas like machine learning, finance, engineering and all. Now when any new algorithm is proposed, this algorithm performance is tested. So before applying these new algorithms to real life problems, researchers often use benchmark test function to check algorithm performance and its effectiveness. Here you can see commonly used benchmark test functions for algorithm testing. These functions help test new algorithms to understand how good they are and where might they struggle. Now next question is how algorithm testing is done. This we will try to understand using a comparison. Here you can see one side we have new car model testing in real life, other side we have new algorithm testing. Now step by step we will understand how we can test new algorithm, then how we can calculate mean and standard deviation of benchmark test function for new algorithms. Now let's start it. So here we have this simple comparison. For example, car testing in real life. Before launching a new car model, manufacturers conduct various tests to ensure car performance, efficiency, and its reliability. Similarly, before applying Meta-heuristic algorithms to real-life problems, we test them using benchmark test functions. So here you can see simple comparison. One side we have car testing in real life and other side we have algorithm testing. So first we will check the performance. So we have performance testing. We will check the speed and efficiency for both car and algorithm. During car testing, engineers measure how fast a car can accelerate and also test the fuel efficiency to see how much energy a car consumes. And on the other side, we have algorithm testing. Now we have algorithm testing. During algorithm testing, we measure how quickly an algorithm finds the best solution, that is the algorithm convergence speed, how fast it converges on the optimal point, that is the best solution. Suppose we have two algorithms, algorithm A and algorithm B. If algorithm A finds the optimal solution in 10 seconds and algorithm B takes 50 seconds to find the optimal solution, then we will consider algorithm A is more efficient. So here algorithm A is more efficient as comparison with algorithm B. Second point we have algorithm robustness. For example, during car testing in real life, cars are tested on different smooth roads, mountain, and snowy conditions to ensure they perform well in all situations. And during algorithm testing, we test algorithm on different benchmark test functions. And in benchmark test functions, we have both easy and hard optimization problems. Using this, we will check their robustness. For example, if your algorithm solve sphere function easily but struggle on other function, then it is not a robust optimizer. Like in real life, if your car well on highway but struggle on hills, then it is not robust car. Same if your algorithm is doing well for few functions and it is struggling with other, then it is not a robust optimizer. Third point, we have avoiding local minima. So in real life, during car testing, cars are tested on city roads with traffic. During car testing, cars are tested on city roads with traffic to check how well they maneuver. And during algorithm testing, we try to avoid local minima. And in benchmark test functions, some function have local minima, means traps in optima. So we test if the algorithm can escape these and reach the global best solution or not. So algorithm must avoid getting trapped in local optima. Next point, we have best, worst, and average performance. During car testing in real life, cars best speed, worst efficiency, and average fuel consumptions are recorded. And during algorithm testing, we calculate mean, standard deviation, best and worst results. Why? To analyze the algorithm performance. And if your algorithm performance varies too much across different runs, it is not reliable. For example, during car testing, if fuel efficiency varies too much in different conditions, then it is not stable. Then we have comparison with other models. During car testing in real life, we often compare the car performance against other cars in the market. Same during algorithm testing. Here we will compare the new algorithm performance against existing algorithms. This you can see for every new algorithm that is proposed. You can see tested on benchmark test function, and then its performance is also compared with well-known algorithms. Because if new researchers claims their new algorithm is better, then they must prove it. So to prove this, we compare algorithm performance with the existing algorithms. Why we are using benchmark test functions? They are like a test track for algorithm, just like a test track for cars. So meta-heuristic algorithms are tested on benchmark test functions before being used in real world. Next question is how we can calculate mean, standard deviation for benchmark functions. Now it is clear that when evaluating optimization algorithms, we use benchmark functions to measure algorithm performance, and to ensure a fair comparison, we calculate mean and standard deviation from multiple runs of the algorithm. So why we are calculating mean and standard deviation? For fair comparison. Now step by step we will calculate mean and standard deviation. Suppose here we have optimization algorithm ACO and we run this algorithm on benchmark test functions. So first benchmark test function we have here sphere function. Now n time we will run ACO on this benchmark test function. Suppose we will run this algorithm 30 time. Now value for n we have 30. It means 30 time we will run this algorithm on this sphere function. You can see here each run gives a different final value. So first we will calculate multiple runs of the algorithm. Suppose we run 30 time ACO on sphere function. Now we will record the final function values. Here you can see final function values after 30 run on sphere function. We have x is equal to 0.0012. This is the algorithm value, that is ACO value on sphere function. First run, second run we have 0.008. Third time when we run this algorithm on the sphere function, value we have 0.0020. Like that, 30th value we have 0.0013. So here each value represents a solution quality found by algorithm in particular run. Now next step we will calculate the mean, that is average. So mean represents the average performance of algorithm across multiple runs, and we will calculate mean using this 1 by n. N is the total number of runs then we have its average. So for simplicity we will take here 5 run, because for 30 run it will be a little bit complicated. Just for simplicity we will take 5 runs. So we have value for n now 5. Done. So now we will consider the value for 5 run. You can see x, that is 0.0012 in first run, second run 0.0008, like that we have values for 5 run. Now we will calculate the mean, that is the average. So here we calculated the average, that is 0.00132. The next step we will calculate the standard deviation. So we use standard deviation to check how much the values deviate from the mean. Here you can see we calculated the mean value. Now using standard deviation we will check the how much values deviate from the mean value, that is the stability or the reliability of the algorithm. So we will calculate the standard deviation using this. Here you can see n, capital N, that is the total number of runs. We have 5. I we have 1 to n. So 1 to n means 5 run. X1 means algorithm value in first run, that is 0.0012. X2 algorithm final value in second run, that is 0.008. X3, that is the algorithm final value in third run, 0.0020, like that we have for 5 run. And here you can see mu, that we already calculated in previous value. The value for I we have 1 to n. So here we calculated the value for mean, that is 0.00132. Now we will put the values here and calculate the standard deviation for 5 runs, that is 0.0129. So here low standard deviation means algorithm is consistent, means algorithm is producing similar results in each run. And if you're getting the highest standard deviation, it means algorithm performance varies a lot between runs. So we can calculate mean and standard deviation using Python. Here you can see means this is the result from 30 run of the algorithm on the specific function. Then we will calculate mean and standard deviation. So here why mean and standard deviation are important. Mean is show how well the algorithm perform on average. Lower mean indicate better optimization results, and standard deviation used to show how stable the algorithm is. If we have lower standard deviation, it means algorithms consistent performance, and if we have higher standard deviation means high variation and instability. So here we have test function, that is the sphere function, then algorithm. Now we will compare this algorithm results with other algorithm. So we have function as sphere function. On same function, these two algorithms are tested and then results are compared. So we'll compare mean values, best, worst, and standard deviation values. You can see here for this algorithm, mean value 0.00145, best we have 0.008, and worst we have this one. And after this we will observe if we have lower mean value, it means it generally find the better solution, and if we have lower standard deviation means it is more stable across different runs. So why we are using benchmark test function to test optimization algorithm. How we will test the algorithm? First we will run the algorithm multiple times, then collect the function values. After this we will calculate mean, that is used to measure algorithm performance, then standard deviation, that is used to check algorithm stability. Done. So here you can see simple steps how we can calculate mean and standard deviation. First we will generate random inputs within the functions domain, then we will evaluate function at those points. After this we will calculate mean and standard deviation for function values. So that's all about this video. If you have any questions you can comment below, and thanks for watching this video.